Okay, welcome everybody to this series of lectures on communication systems. Today in part 1 we'll be learning about amplitude modulation. So before we start the class, let's first try and understand what is the need for modulation, or in other words, what is the advantage of modulation. The first one is we cannot transmit audio over long distance, right? If I'm speaking to you in a class, I don't require any amplifier. I can speak at a loud voice so that each one of you can hear what I am saying. But say if you are all sitting in a huge hall or an auditorium, I can use an audio amplifier where I can amplify my voice and ensure that each one of you are able to hear me, right? But then if you are not in Hyderabad at all and I am speaking in Hyderabad, then obviously I cannot amplify my audio signal and transmit it over long distances, okay, to different cities. Okay, that is not possible. So what do I do? So I can superimpose my audio into some RF signal, and the RF signal can be transmitted from one place to other, and the receiving end, so that RF signal you can demodulate it and you get back your audio. Okay, that is what we are doing right now through this online mode of classes. Okay, the second advantage is multiplexing. Okay, what is multiplexing is like in bits you have several professors talking simultaneously in all taking different classes. So obviously they are all speaking in the same audio range, 0 to 4 kilohertz. Okay, because what human beings, when we speak, it is 0 to 4 kilohertz. Otherwise we can hear up to 40 kilohertz. So all the music components what is there, they are above up to 40 kilohertz, up to 30 kilohertz. So that is why when we speak, human voice is more or less confined to 0 to only 4 kilohertz. That is the reason if you see in the mobiles and all, if you try to transmit music what is being played, so you won't get that quality, because they are mobiles and all are essentially meant for voice communication, and they transmit only limited number of frequencies. So the higher frequencies they get attenuated. Okay, whereas when you're hearing a live band or something, right, and so you will hear the entire frequency spectrum, so it is a rich music. Okay, so coming back to multiplexing, so when all these audio signals are being multiplexed, there are n number of professors, so each one is speaking in the same frequency audio band, but what we can do is we can put each of them in a different carrier frequency. Say one professor's audio, you can put it in say 100 megahertz, the other one in 125 megahertz, 150 megahertz, so on and so forth, and you can transmit it, and the students who want to attend a particular class will tune into that particular frequency. So that is what the advantage of modulation is. You can do multiplexing. And one more advantage what we see out here is antenna size. So as you keep increasing the frequency, the size of the antenna decreases. So when we learn about antenna theory, you will realize that the physical size of the antenna is inversely proportional to the frequency, or it is directly proportional to the wavelength. So high frequencies means lower wavelength and lower antenna size. Okay, so this is why we go in for modulation. So one of the most common and easy scheme of modulation is amplitude modulation. So what here we do is, if you see here on top, you have an sinusoidal signal. This is the speech signal, or you can call the source signal, which is requires to be modulated, and this is the carrier, which is the RF signal. Okay, so generally in textbooks a sinusoidal signal is shown here just for illustration purpose, and this need not be pure sinusoidal. When I am speaking, okay, my signal is not going to be pure sinusoidal, it is going to be a mix of frequencies from 0 to 4 kilohertz. Okay, so this is showing only one particular frequency. Okay, that doesn't mean always in an amplitude modulation it will be an sinusoidal input here, right? It will be a complex signal comprising of signals which is band limited. Okay, it will be much lower than the carrier wave. Okay, the max frequency available in the source signal will be much lesser than the carrier signal. So this is the carrier wave. So in amplitude modulation, the carrier signal amplitude is varied, which is proportional to the signal which requires to be modulated, which is to be modulated. modulated. Okay, so this is the carrier signal and this is the modulation signal. If you see, this is the final AM signal. The carrier amplitude, okay, is being modulated based on the input signal out here. Okay, this is the signal, message signal, you call it as message signal. So based on the message signal, the amplitude of the carrier here is being modulated. Okay, you don't see this green line, okay, you just see the red wave form which is being transmitted. Obviously this is just indicating that the amplitude is being varied in this pattern. Okay, so this green line is not transmitted, only the red line, okay, which is the carrier which is modulated, this is been transmitted. So this is known as a simple AM modulation. So let's see how to generate an AM signal. Okay, this is a normal amplifier with a gain G. So this is the carrier signal. Okay, AC is the magnitude of the carrier and this is the frequency of the carrier, cos C omega t. So this represents a sinusoidal signal. Okay, so this is the gain of the amplifier G. So the output will be AC G cos omega t. So what I want to do is how to generate an AM signal. I can make G a function of the modulating signal. Okay, so if I make G proportional to my modulating signal, this carrier will the amplitude of the carrier will change as. Okay, so let me do something. This is an inverting amplifier which you might have studied in your analog class. Okay, so let's just revise how this functions. Okay, to analyze an op amp is pretty easy. There are only two fundamental concepts. Okay, one, when it is connected in a feedback. Okay, when the op amp is connected in a feedback topology, okay, the input and the output will follow each other. Okay, that means in case you have given a ground here, this terminal also will be at a ground potential. Okay, these two will try to follow each other in an op amp, and that is only when it is connected in a loop in a feedback network. Okay, where you have to give a feedback. If you give it in an open loop configuration, then that will not happen. Whenever you give a feedback, it will try and adjust the voltage in such a manner that these two voltages will be equal. Okay, the second rule of an op amp is no current can flow into the terminals of the op amp because it is a very high impedance module. Okay, so no current will flow into the op amp. So if you apply these two rules, you will be able to analyze any op amp circuit. Okay, excuse me. So this is an inverting amplifier. Now we'll just see why it's known as an inverting amplifier. You have applied a voltage out here, V in. So the current, so obviously this is going to be ground because you are connected ground here. Op amp, I said both these terminals will be at the same potential. So this is going to be ground here, and no current can flow here. So what is the current which is going to flow from here? So V in by R in. So that is the current which will flow here. Okay, now that current cannot go here, right? So that current has to come here. Okay, now if I try to find out the potential across RF, it is the same current. Okay, now whereas what this is, if you see the direction, it has to be from left to right because this current is going to come from left to right. So this current also has to go from left to right. Now this current has to flow like this. So now that current, if I try to equate, it will be 0 minus V out by RF. Okay, so here it is V in by R in. So if you try to equate both these things, you will get gain as V out by V in minus RF by R in. That is, the signal gets inverted, but the gain is given by RF by IN. This is a simple inverting amplifier. How it works. Now how do I use this to generate an AM modulation? Okay, the only thing which I need to do out here is replace this RF, okay, with some device, okay, whose resistance will vary with an gate signal which is applied here. So suppose I am using a PJFET or a PFET, its resistance changes with the gate voltage which is applied here. Okay, so it has to vary inversely. Okay, so you can use some PTFET, so that's not very important. Okay, now so what happens is, now the gain, if you see, the gain can be, the output can be defined as an input into R in by RF, right? So and this is RF. Now this has been RF by RN. Okay, RF by RN. Okay, now this is the voltage gain, right? V out is equal to RF by Rn into Vin. Now instead of RF, okay, now since we are going to use a device whose resistance is going to be proportional with the input signal which we are applying, so I am just replacing that RF by Rin with a constant K, and now I am introducing this term Am cos omega t. That means this resistance is going to vary with Am cos omega t, so I put a factor of K. So that means the gain is going to change. So I am going to get an output which is K Am cos omega t into this is the carrier input signal. So this is the input signal which is being amplified by a factor K Am cos omega t. Okay, so don't try to mug up this circuit. We'll now slowly realize that this is a very stupid circuit. It has got lot of problems in this. So I have just told, okay, this is the easiest way to generate this particular signal. That's all. Okay, I just want to tell you at this point of time that this is how we generate this particular waveform. Okay, but this is not the right way to generate it. That we will see very shortly. Okay, now how to demodulate this signal. So I am going to transmit Am cos omega t, okay, into AC cos omega ct. Now how to demodulate it? Okay, that was been transmitted, so I need to have a receiver which is placed far away from the transmitter. Now I am receiving that signal. Now how to demodulate it? Demodulate means to get back the modulating signal, right? We don't want the carrier, we want the audio signal back, right? So let's try to make a circuit which will get back that. So let us try to so assume that there is a mixer out here. Okay, this is the demodulator. In a mixer, what it does, we are going to multiply this input signal with one more signal, and I am assuming that at the receiver end also I have an carrier here, AC cos omega ct. So this was the carrier which we use in the transmitter. We are using the same carrier signal at the receiver end also. I am going to multiply these two. So if you multiply these two, what happens? So this is Am cos omega t cos omega ct AC, and again we are multiplying with AC cos omega ct. Okay, so once you see, you can write this is all the DC part, so this is not of very consequence. So now you have cos omega t, right, and you have a cos square omega ct, which I can write as 1 plus cos 2 omega ct, right, because you have cos square. So if you have cos square, I can write as 1 plus cos 2 omega ct. So there is a 2 out here which is put here. So now I'm going to open up this bracket. So I have two signals out here. Okay, these are the magnitude, these are only the gains. So this we are not going to focus on that. We are essentially going to focus on what frequency is available to us. Okay, once I open the bracket, I have two signals out here. Okay, so what is this signal? Cos omega mt, right? What is this? This is actually my signal, this was my original signal, right? This is what I use for modulation. That means this is my required signal. And what about this? This is 2 omega ct cos omega mt. That means twice the carrier frequency. This is twice the carrier frequency which is being modulated by an cos omega t signal. Okay, so I just want this. I don't want this signal to be there. Finally, so what I do, I can use a low pass filter, right? Low pass filter is which allows low frequencies to pass. So this is the notation for low pass filter. If you see, okay, it means the high frequency is stopped and the low frequencies are allowed to pass. So this is the notation which generally we use for low pass filter. So that is being passed out here. Now if you do that, you can easily block this component. Okay, this is, if you see this component, what is this actually component is 2 omega ct. It is twice the carrier signal which is modulated by that signal, and this is the required signal, baseband signal. You also call it modulating signal or the baseband signal. So that is available. So you get this signal out here. Okay, so I'll demonstrate you this in the next video lecture through an LT spice simulation also. So it will be pretty clear to you. Okay, so you see, okay, it is pretty easy, right, doing like this. So then I said ki, okay, this modulation is kind of a stupid scheme. Okay, so I'll now explain what is the drawback of doing all these things. Okay, now initially we assumed that that the signal which is available in the receiver is the carrier signal, right? But that cannot be always true, right? So you are generating some carrier wave at the transmitting side, and you are generating some carrier wave in the receiving side also. So they need not be exactly of the same frequency, right, and the same phase. So assume there is a delta variation from the desired frequency at the receiver side. Okay, so the transmitter frequency and the receiver frequency are differing from each other by a small magnitude called delta. right? Now you multiply these two signals, so Am cos omega ct, you will get like this, right? This is the equation which you get, right? And then you multiply all these things and do little bit of mathematical manipulation. What you will get is once you pass from the low pass filter, you will get this cos omega t and cos delta t. Okay, once you if you multiply these two, okay, like if you multiply these two, what do you get? Now cos omega cos cos a into cos b, cos a plus b into cos a minus plus cos a minus b, you will get those terms, right? So a plus b will give 2 cos omega t, right? Plus delta, and a minus b will give only delta. Okay, so that delta which is available with cos, that term is available here, whereas the next term cos 2 omega ct, that will go 2 omega ct plus delta along with cos omega t, that becomes a high component which gets filtered out in the low pass filter. So you have this this is coming out of the low pass filter. Now if you see here, what is this cos delta t? Okay, so this is going to create a noise here. Okay, this is again in the baseband only. This signal, this cos delta t will be in the voice signal band itself, so that is, you cannot filter out this delta. This change, the difference in between the transmitter and the receive frequency, that comes as cos delta, and that is going to create noise in the output waveform. Okay, and this is not going to be a constant, right? Because you have a transmitter which is continuously transmitting. Say you have in the transmitting side, you have a carrier of 120 megahertz, right? So that may not exactly transmit at 120 megahertz. Okay, even with the time, it might change to 120.001, 002, and with temperature and things like that, it will slightly keep varying. Similarly, in the receiver side also, that local oscillator will there will be small oscillations within the tune. Even if you have tuned it, it cannot be perfect, it will keep changing. So those two, the difference between the transmitter and receiver local oscillators or the carrier signals, will continuously generate noise, okay, here as cos delta t along with the modulation signal after the LPF. So this is entirely not a very ideal situation. So I will not transmit this signal, I will transmit something else. So let me now go back to our design and let's change the way we are transmitting signals. Okay, now so for that, let me just explain you what is an it should be non-inverting amplifier. Okay, I have written inverting amplifier. This is a non-inverting amplifier. Okay, where I have an Rin and I have an RF. So if you try to see the same philosophy here, where the input voltage at the plus and minus of an op amp remains same, the voltage out here will be V in, right? So the current which will flow into R in will be V in divided by R in, right? And the same current, it is going from here from right to left. So that same current has to come from here, because op amp input of terminal, they can't be any current going into the input terminal. So that current. So now if I try to equate this current, it will be V out minus V in by RF. Now if you try to simplify that, you will get a gain which is 1 plus RF by Rin. Okay, so here you will find both are in phase, like there is no inversion happening. So whatever input signal you give in the plus, okay, you will get an the same signal at V out. Okay, if you take V out, it will be 1 plus RF into V in, right? So V in goes in that side. So the gain will be 1 plus RF by Rin. Okay, so now if you try to make generate an AM signal like this, wherein the Rin, you are now using an FET and you are making Rin a function of inputting signal, right? So here Rin, you are making Rin as 1 by R, you are making inversely proportional to the modulating signal, because this is an FET where if you give an increasing signal, the resistance will drop. Okay, because you are biasing, you are switching on this transistor. So if you give an increasing signal, the resistance will decrease, and if you give lower signal, the resistance will increase out here. So it becomes an Rin, so will become K into K, Rin is proportional to K by V in, so that will come into the numerator. So let me go back, here. So in fact, what I'm going to generate here is, if you you have, since you have a factor of 1 here, V out is V in into 1 plus RF. So what does this 1 do here out here is, you are inserting an additional component which is pure carrier, and then carrier which is again modulated by an modulating signal. Okay, so this is the actual AM signal and this is the actual AM circuit, right? It has got two unique components. One, it is carrier. So initially we started off with only calling this as an AM, which was wrong. Now I am calling this as AM. Okay, so it has got a carrier signal plus and carrier signal modulated by a modulating signal. Okay, this got two components, AC cos C omega t, which is carrier signal, and AC cos C omega t multiplied by AM cos omega t. So this is known as the modulating signal, right? So it has got two different components. So what is the advantage of having these two components? We'll see that very shortly. Okay, so it has got this simplifies our receiver design, and the problem which we encountered in our receiver design because of the mismatch in frequencies between the transmitted and receiver frequencies, that will be eliminated. So we'll see that shortly. So now this is going to be my AM signal. Right, this is another circuit which will help us in generating AM signal. So this is looking very complicated, but it's not. It's actually an differential amplifier. Okay, it's a simple differential amplifier where you have inputs. One of the inputs is grounded here. Okay, AC grounded through a capacitor, and you are giving an RF input, carrier input out here, and the gain of this amplifier is controlled by the bias current which flows into this, which is known as the tail current here, right? So in that tail current is been controlled by an input signal which you are giving out here, right? So this is the modulating signal. So the modulating signal essentially changes the gain of this amplifier. This is a differential amplifier, and you have two resistance here because you are tuning it to the required frequencies. You don't want spurious signals out here, so this will just tune it to the only the required frequencies, whatever is the carrier frequency. So that frequency will be picked up here in the output. Okay, so if you have to understand more about how a differential amplifier works, and there is another series of lectures which is there in my YouTube channel and known as analog electronics. So there I have started with CE amplifier, and then I have gone about till differential amplifier. There are 4 videos, so that will allow you to understand more about the circuit operation of this modulator. Okay, essentially you need to understand that there are two components in AM, which is AC C cos omega CT plus AC cos C omega t modulated by AM cos omega MT. Okay, so this is the modulating signal and this is the carrier. So once we have generated it, now if you see the demodulation part. Okay, so this is the signal which we are transmitting now. Initially it was only this much. Now we are going to transmit that and plus the carrier, and an additional component of carrier we are going to transmit. Now if you try to, let's do some mathematics before we see the circuit implementation. If you just square it, what happens? Okay, this will give a square cos square omega ct. Now cos square omega ct is 1 plus 2 cos omega ct, right? So 2 omega ct, if you pass it through a low pass filter, you can isolate 2 omega ct. Okay, and then 1, that is 1 will give an a square C by 2. Okay, that is a DC component. Okay, that we will neglect that. There's DC components, don't matter here. And what about this component? Let me take this square component. Again, it has got a square m cos square omega m plus a square cos square. Okay, now if you see, they are all square, so these also will become 1 plus 2 cos omega m and 1 plus 2 cos omega ct. They are all higher components. Okay, so that can be again we'll filter out those. What about the middle term? If you see, it is a square c am and cos omega ct and cos omega mt, right? Right, this is what okay, there has to be a square here, right? 2ab, right? 2ab, so there has to be a square here. I missed it out. So there has to be a cos square omega t. So that cos square omega t I can write as 1 plus 2 omega ct. So that one along with this cos omega mt, okay, will generate and baseband signal here. So if you pass it through a low pass filter, so you will get 1 cos omega mt. So this is going to be a high frequency component. This is also going to be a high frequency component. Here there is a cos square which I can write it as 1 plus cos 2 omega ct. So that 2 omega ct again is an high frequency component, but that one along with this cos omega t will be the baseband signal. Okay, so I can easily filter out that signal here. Now I don't have to multiply it with cos omega ct at the receiver end. Okay, I just have to do a square and I will be able to get an cos omega m signal. Okay, so that is the important thing. Earlier, without this component, there was a requirement of multiplying it with this signal here. Now with this signal being sent already from the transmitter, now I just have to do a square operation. Okay, so that square operation will do this 2ab. Okay, it will multiply this cos omega ct with cos omega ct. Initially this cos omega ct was not there, so I was multiplying this cos omega ct with another cos omega ct being generated at the receiver end. Now I am sending it from the transmitter side itself, so I am just squaring it. If I am squaring it, okay, that 2ab, right, a plus b square is a square plus 2ab plus b, so that 2ab factor here, this cos omega ct will get multiplied with that cos omega ct. So that is doing it within itself without the requirement. So that signal what is being transmitted is being used to multiply here and get back my baseband signal. So that is how. So now you have a baseband signal. So how to do this multiplication? So you don't require to have a complex multiplier also. You can just put an diode. Okay, so diode is not a linear component. You know what is linear, because whatever if I give VE in and if the output is K into V in, it will known as it will be known as a linear component. Okay, whereas diode, it transmits only in one direction, so it introduces non-linearity. So whenever there is a non-linear component introduced into the circuit, it generates harmonics. Harmonics means higher frequency components. So obviously when you are applying this signal out here, okay, the top one, so it will generate the square and cube root and all those signals out here, right, and then it will generate all those signals, and one of the components out here will be only cos omega mt also. Okay, and so we can filter out only, you can push a low pass filter which all signals above cos omega mt will be attenuated, on only signals those who are above below cos omega t will be passed. So if you do that, you will be able to get your baseband signal or the modulating signal out here, right. So here the values of RC are component, right, are very critical, right. If you use an RC value, okay, which is much greater than carrier, so that the carrier waveform is not reproduced here, but it has to be less than 1 by omega m, right. RC has to be less than 1 by omega m, which this is the modulating angular frequency, right. So that it can follow, this RC value has to follow this waveform on top, but it should not follow the this carrier signal waveform. So you have to judiciously choose the value of RC. So that is an LC filter. This is basically an RC low pass filter. Okay, for high frequencies, you know what is the impedance of a capacitance is 1 by C omega, right. So for high frequencies it will be low impedance, so the output will get shorted here, it will not get reflected here, right. So for low frequencies, okay, this 1 by C omega is in the denominator, omega is very large, so it will not get shorted out. Okay, so you are putting a high impedance, so that output will be available. So this is how it works. So this is the value. So probably in the next video I'll show you these simulations in LT-Spice and the effect of variation of RC, what happens. Okay, those things I'll demonstrate to you. Okay, so this is how. So now you understood why this AM signal has got these two components. It makes our life easy at the receiver end, right. So the receiver design has become pretty simple. Okay, now let's do a little bit of mathematics to understand more about amplitude modulation. Okay, so this is the message signal or modulation signal or baseband signal. These are the various terminologies we use. AM cos 2 pi FMT. Okay, this is the carrier signal. AC cos 2 pi FCT. Now what is the AM signal? AM we have defined as, this is the carrier signal plus the modulating frequency into the carrier frequency. Okay, it is a product of these two, whereas these two components are there, two different components. Okay, now if I take AC common out here, that is the the magnitude of the carrier, if I take it as a common, I introduce a term and also I take out the frequency component outside the bracket, then I have a term called M coming in here. M is nothing but AM divided by AC, which is also known as the modulation index. So this is again an important parameter in amplitude modulation, given by AM, that is the amplitude of the modulating signal, and AC is the carrier signal. Okay, so modulation index K is the measure measure of the extent to which the carrier voltage is varied by the modulating signal. Okay, if M is equal to 0 means there is no modulation, M is equal to 100 means there is 100% modulation, and M greater than 1 becomes over modulation. Okay, that will be clear in the next graph. Here it is M less than 1, this is the carrier signal, it is being modulated, so this is M is less than 1. In this case M is equal to 1, right? It is almost the carrier, right? When the carrier signal, when the modulating signal is maximum, you find carrier signal amplitude is almost 0, or it is 0, you can say, for M equal to 1. Whenever M becomes more than 1, you will find that the signal gets distorted out here, so you won't be able to get back your signal here. So you have to be careful that your modulation index is always less than 1. Okay, so that is a critical pair. Now how do we measure these values of modulation index? So if you see an AM signal which is coming out here, if you put it into an oscilloscope, you will be able to measure the E max. E max is this, where the carrier signal is maximum, and E min is this maximum. Okay, where the minimum, E min is the minimum value of the carrier on both on the positive side. Okay, this is the minimum and this is the maximum. So if you see what is V carrier, V carrier is nothing but average of these two signals, right? It will be V EM max, right, plus E max plus E min by 2, you will get the carrier signal. Okay, whereas what is the modulation signal, if you see, okay, this so it will be E max minus E min by 2 because E max minus E min will give peak to peak, but we are speaking of only the peak value, so it will become E max minus E min by 2. Okay, whereas the carrier signal is this is the average V carrier signal, right? So here you will find E max plus E min by 2 will give you the carrier signal, right? So if you see the modulation index, you can which is Vm by Vc, which will give you Vmax minus Vin by Vmax plus Vin. So this is how, by measuring in an oscilloscope, you can find out the modulation index. So this is the formula. Okay, so this formula you need to remember for your various exam point of view, and physically also, when if you are doing a practical experiment, this is how, when you put it into an oscilloscope, you compute the modulation index by measuring these two values. Okay, so that is about modulation index of an AM signal. Now coming to power and bandwidth of an AM signal, right? Now what we do is this is the signal. Okay, this is the carrier signal, this is the AM into, right, modulating signal into the carrier signal. This is the standard definition of AM signal. Now I am replacing this AM with MAC out here. Okay, and then I am going to take this is cos A into cos B, so I am going to write cos A plus B into cos A minus B by 2. Okay, so I have put this. So what does this mean? Okay, this equation means that actually this has got here we are writing it in the product form, but if you write it in this form, what we can visualize it, this actually the signal what we are going to transmit has got 3 frequency components. Okay, one is FC, okay, which is the carrier signal, which has got an amplitude of AC, right? Then you have got one more frequency component, which is FC plus FM, that is the carrier which is displaced by the modulating frequency FM, and M by 2. Okay, that has got an amplitude of M by 2 AC, right? And another component also we have, okay, which is FC minus FM. So you are in fact you had initially one carrier frequency and one modulating frequency, and when you make an AM signal, it actually we are sending 3 different frequency components with each having different amplitudes. Okay, this is the amplitude for that, this is the amplitude for both these two signals, okay, which is one is FC plus FM FM and FC minus FM. So what is the total bandwidth which is required? So bandwidth is the 2 FM, right, which is 2 FM. Okay, this M should be suffix out here. Bandwidth is 2 FM, that is from FC plus FM to FC minus FM. That is the bandwidth which is required. Okay, or you can call it from FC minus FM to FC plus FM. Okay, this will lie in between that. Okay, this frequency. So this is the total bandwidth requirement, that is 2 FM. So the bandwidth for an AM signal is 2 FM. Now what is the power which is required? Now let me call the power of the carrier. Okay, this is the voltage, right, VC. That is the peak voltage, right, for an cos signal, that is peak signal. So what is the RMS value? It will be AC by root 2. And what is the power? Power is V RMS square by R. R is the resistance. Okay, here we are assuming the resistance to be 1 here for power calculations. So what will be the power? It will be AC by root 2 the square. So that will be AC by 2, AC square by 2. So this is the power. Okay, this is the power of the carrier. This is the carrier power. Okay, that I am, so this becomes PC out here, right? And this is M by 2 AC. Now if I take M by 2 AC for this and M by 2 AC for this. Okay, so M by 2 AC by 2, if I do this by root 2 the square. Okay, so if I do that, I will get M square by 4 PC. If I am going to replace AC square by 2 by PC, I will get M square by 4 PC. Okay, and also the power for this also I will get M square by 4 PC. So this is known as the upper sideband. This is known as the lower sideband. This is known as the carrier power. Okay, so now if you see, PC is the carrier power, M square by 4 is the upper sideband power, FC plus FM. M square by 4 is the power by the lower sideband. Okay, so the total power comes out to be PC plus M square by 2 PC. Okay, so this is the total power which is required to be there for transmitting an AM signal. Right now, if you try to find out what is the max power efficiency, so max power efficiency is the signal power divided by the total power. Okay, so when I say signal power, it means the power which contains useful information. So in this case, the information is available only in these, right, the modulating signal. In this signal, there's no modulating signal, so I can't say this is my signal power. So I'll call the upper sideband and the lower sideband as the signals which is conveying the actual information, actual signal. Okay, whatever I am speaking, or this is the modulating signal which is there. So that is the reason why I call these as the required power or the signal power, and this is as the carrier power. Okay, and together you call them as a total power. So the signal power is M square by 2 from here. Okay, M square by 2 is M square by 4 of the upper sideband and M square by 4 of the lower sideband. So you do that. Okay, you know M square by 4. Now if you put the value of M equal to 1, that is for modulation index of 1, you will get 33%. So you will find this is the maximum power efficiency. So obviously the efficiency of an AM signal is not that very good as compared to the other modulation schemes which we are going to see shortly. Okay, so this is how the power and the bandwidth of an AM is defined. Okay, now this is showing the frequency spectrum. This is the frequency. So you will have an carrier signal. Okay, at FC, that this is the x-axis is the frequency. So FC is the carrier signal. Okay, it will have an amplitude of VC. Then you have FC minus 1 and FC minus FM and FC plus FM. These are another two frequency components which will be there. Okay, so there are three different unique frequencies which we are going to which is going to be there in an AM signal. So this will have an amplitude of MVC by 2 and MVC by 2. Okay, this comes from this equation, right? From this equation there are three frequency components. That is what is shown here. So the total bandwidth here you can clearly see is 2 FM. So this is the 2 FM. Like suppose I am sending an 100 megahertz signal, and I am using an 1 kilohertz tone which I want to transmit, then this will be 99 and this will be 101. So 99 to 101, it is 2 kilohertz. Okay, 2 kilohertz, not kilohertz, right? I'm speaking of if I am going to send 100 megahertz, then kilohertz will be 100.000, 100.99.99, right? 99 0.999 megahertz, I can call it that way, and this will be 100.001 megahertz. Okay, so the bandwidth will be 2 kilohertz here. So FC minus FM and FC plus FM, this is going to be the bandwidth. Okay, now not necessarily, like I said, till now we were speaking of only one signal. Like when I am speaking, okay, my voice signal can have a 0 frequency or say 100 frequency to 4 kilohertz, anything, right? So this is how the bandwidth will look like, right? So my 100 kilohertz, now when I am speaking, it is an actually I am speaking an sum of, there is so many signals which are there, various and I am not speaking on a single tone. There are various frequency components. So all those frequency components will be available here. Okay, so this is the maximum 4 kilohertz. Say if it's the maximum, this is the carrier frequency. This will be carrier frequency minus 4 kilohertz and carrier frequency plus 4 kilohertz, but there will be lower components also. So all those lower components also will be here, available here. So however the total bandwidth remains. To compute the total bandwidth, you have to write 2 FM. FM means the maximum modulating frequency available. Okay, so that is the bandwidth of an AM signal. Now this is a small example so that to make things more clear to you. Determine the maximum sideband power if the carrier output is 1 kilowatt and calculate the total maximum power transmitted. So it says ki sideband maximum sideband occurs when modulation K, some books they use the value K for modulation index, so it is written as K here, and here in this side, okay, since the power is proportional to the square of the voltage, it has 1/4 of the carrier power, right? So m square by 4 we know, right? That is the carrier power which is available in each sideband, and m square by 2 is in both the sidebands plus together. So if 1 kilowatt, so m square by 4, m is equal to 1, so 1 by 4, so 250 is the power available in upper sideband and lower sideband if carrier is 1 kilowatt. So the total power will be 1 kilowatt plus upper sideband plus lower sideband, so it will be 1.5 kilowatt. Okay, so let's take one more example out here. It says a 400 watt carrier is modulated to depth of 75%. Calculate the total power, right? So the carrier PC is given as an 400, and we know the total power is given by PC into 1 plus m square by 2. So m is given as 75%. 75% is 0.75, right? M, the value of m, 75%, it is percent, so m will come to 0.75. so if you compute this, you will get a total power of 512.5 watts. Okay, so let's take one more last example. So this is the modulating signal. 10 cos 2 pi 10 to the power of t is the amplitude which modulates a carrier. 50 cos 2 pi 10 to the power of 5t. Find the modulation index, carrier power, and the power required to transmit the AM. Now from this equation, it is very clear. AM, okay, the amplitude for the modulation signal is 10 volts, right? Frequency of the modulation signal here is 10 to the 2 pi ft. So f is to 10 to the power of 3. So I take 10 to the power of 3 is 1 kilohertz. So bandwidth will be 2 kilohertz, right? So bandwidth will become 2 kilohertz out here. Amplitude of the carrier is 50. So I write 50. From here I can see 10 to the power of 5 is what? Is 100 kilohertz. So 100 kilohertz. Okay, this is the carrier. Now if you see the bandwidth, okay, it will be from 100. Okay, 100 minus 1, from 99 to 100 plus 1 to 10. So this is the 2 megahertz bandwidth in which this signal will be there. FC plus FM and FC minus FM. So that is the band. Okay, now modulation index is AM by AC. So that is given as 10 and then 50. 10 by 50 you get 0.2. The carrier power is AC square by 2R. Okay, this is AC. AC square, the amplitude will be 50 by root 2. Okay, RMS value. So 50 by root 2 the square. So you get an AC square by 2. Then R we generally take it as 1. So R is, so you get, this is the power. Okay, so once that total power you get to calculate PC into 1 plus mu square. Mu, again mu is another term which we keep using for modulation. It is an M square, right? M square or mu square or K square. Different textbooks use a different notation. So this is mu is nothing but the modulation index which we calculated here. So you put that formula, so you get the total power. Okay. Now having undertaken those two examples, let's see how an envelope detector. This is known as an envelope detector. Okay, what it essentially does is it tracks the envelope. Okay, envelope means the outer periphery, right? Outer contour. So that is why it is also known as. So this diode essentially rectifies these signals, and RC ensures that only that envelope is reproduced here, right? So this is RC, right? So here you can also see that if you put a modulation index which is greater than 1, the signal gets distorted. So you will get this kind of signal at the output. So you should not do. Also the values of RC have to be very critically chosen. So this RC should not be able to follow your carrier waveform. At the same time, it should not be so high, the product of RC, that it is not able to follow your modulation signal. So it should be low enough to follow the modulating signal, and it should be high enough so that it is not following the carrier signal. So you have to choose the value of RC properly. So it is able to pass only the low frequencies up to omega m, and not pass the carrier frequencies which is much higher than omega m. So you have to choose the value of RC accordingly, right? So that is one way of doing it. The other way, like we said, we should have a local oscillator, right, wherein you can multiply it with omega c, right? This was the first thing we discussed here earlier in the slide, that you can now only problem we said that the local oscillator has to be in perfect sync with the input signal. If there is no phase difference or frequency difference between what is being received, that is that transmitter carrier frequency, and the receiver local oscillator frequency, carrier frequency, then this can work perfectly well. So these are known as synchronous or coherent demodulation. So there are some techniques which will allow us the local oscillator, that means the receiver end carrier frequency generator, to lock with the what is being transmitted. So it is possible for us to whereas this is a very simple design, whereas here it's a complex design where you will use some technique so that the local oscillator frequency is perfectly matching with what is being transmitted. So this is one way of doing it. Like you have an AM signal which is coming in here. It has got two components. I said that it's got a carrier frequency component also. So what you can do is you can use an band pass filter. Okay, so what is coming here will have a carrier frequency, and it will have a lower sideband and an upper sideband. But if you use a band pass filter where you just filter out only the carrier frequency and then multiply that carrier frequency with this frequency. Okay, so essentially this, now since you are not generating it locally, actually you are deriving it from the AM signal itself. So that is why there won't be any phase difference or frequency difference between the receiver and the transmitter, because this is again derived from what is being received itself. So this is one option. Or you can there are something known as phased log circuits. So you can use the phase PLL circuits so that we use this signal out here, okay, the carrier signal out here, we use a local oscillator, and we will try to lock the phase and frequency from what is being received and what is being generated. So that is known as a phase log circuit. So in that case also we can use. So this is known, these schemes are known as synchronous or coherent demodulation. Right, now there are some differences, advantages of diode versus coherent detections. I have just listed out few of them. A diode unable to follow fast modulation properly. Power is absorbed from the tuned circuit. Distortion produced by the diode is not acceptable for some communications. Okay, diode is obviously simple and low cost. In the coherent detections, the advantage, when I write negative, it means it's a disadvantage. Positive means it is advantages. Okay, coherent, the distortion is very less and a greater ability to follow fast modulation, because the diode and RC network is slightly slower. So the modulating signal has to be on the lower side of the frequency spectrum, then only it would work properly. Coherent ability to provide power gain, because in diode you will see it's not an amplifier, whereas in the coherent detection you can use it in an amplifier mode. So it is complex and expensive. These are some of the advantages and disadvantages of diode as compared to the coherent detection scheme. Now you have another modulation scheme which is known as double sideband suppressed carrier. Okay, in which here again we are not allowing the carrier to be transmitted, we are suppressing the carrier out here, right? So why is that we are doing this is essentially we saw that the maximum power efficiency of AM is 33%, right? So you are trying to waste a lot of energy is wasted in transmitting the carrier also. So we are not transmitting the carrier, but the bandwidth, there is no gain in bandwidth here, because you are transmitting the lower sideband as well as the upper sideband. So the bandwidth requirement continues to remain 2 FM, whereas the power requirement comes down drastically. Okay, now this is the signal. Now I am not transmitting the carrier signal separately, so the bandwidth is 2 FM, but the power is now MC square by 4. That one PC which was available here, another additional PC, that is removed here. If you go back to that slide, you will realize that there was one PC factor there, that has been removed. So MC square by 4. So if you see the you can call the modulation power efficiency as 100% here, right? Because there is no wastage. Both these signals contains information of the modulating signal, right? So it is both information signals only. So that is why the modulation efficiency is 100% in this case, right? Now how to modulate this signal? So this is an modulator which is used. You have a local oscillator which is 2 cos 2 phi FCT. This is the carrier signal. Okay, so you are modulating it with MT, and you are also using one more modulator, you are modulating it with minus MT. So this is, you are going to get products out here, right? So if you see this is again a normal AM modulator, you get cos AC cos 2 phi MT plus M by 2 AC this component out here. Here you will get AC cos 2 phi FT, and here it is minus M, because you are putting minus M. So you put minus M. This is the normal AM modulation signal. This is also, now if you try to add these two signals out here, in fact you are subtracting these two signals. So this carrier components get subtracted, and you will have this getting added up, because there is a negative sign here. So this minus minus becomes plus. So you will have only these two, the lower sidebands they get added up, and the higher sidebands get added up, and the lower sideband also gets added up, whereas the carrier signal, pure carrier signals, they get subtracted with each other. So that is not there. So this is how you generate an this is known as double sideband suppressed carrier modulator. Okay, so this is how we do that. So how to demodulate it is, you should have a excuse me a local oscillator. Now in this since you are only transmitting these two components, right, you can't do a square operation. You can't have an diode what we call it as if I go back here, you can't have an envelope or diode AM detector. Okay, you can't have a square operation here, right? So here so this has to be there has to be a local oscillator. Okay, that is the disadvantage. So it has become slightly more complex. You have to have a local oscillator, right? Now how to generate that local frequency, the carrier frequency in the receiver side. So this is a block diagram which is showing that. If you see this is the signal which is being transmitted, AC MT, this is the modulating signal into cos 2 pi FCT, right? This is the modulating signal. We don't have the pure carrier here, only this carrier signal being modulated by MT. So this is the equation, okay, for that. These two equations combined, these two combined I have written as MT out here, right? This is actually FC plus FM. It will have two components, but doesn't matter. Here we are going to write it as in a single form, so easy to understand. So now I have an VCO. VCO is nothing but an voltage controlled oscillator. Okay, so you give an input voltage here. Based on the input voltage, it will generate a frequency. So if you change the frequency voltage here slightly, the frequency also will shift. Okay, that is why it is known as voltage controlled oscillator. Now assuming that this is not perfectly matching with the carrier which is coming here, so there is an difference in the frequency that we are calling it as theta. Okay, so this is the error. Okay, now we want to minimize this error. Okay, we don't want this error actually. Let's assume there is an error here now, theta. Okay, so now you are making this block here. So you are multiplying this is a multiplexer where you are going to multiply these two signals. Okay, cos 2 pi fc you are multiplying with 2 pi fc plus theta. Okay, now if you are going to multiply it, cos A, it is cos A into cos cos A into cos B, cos A plus B and cos A minus B components you will get. Okay, A plus B will give 2 FC component. Okay, and since you are going to pass it with a low pass filter, that will get eliminated, and cos A minus cos B will give cos, and this FC component will get subtracted with each other, and you will have only theta component. So you have MT into cos theta component coming here, right? Cos theta. Similarly, you are doing a 90-degree phase shift here, so you have sin 2 pi FC plus theta out here. You are multiplying it with cos. So cos A into sin B you are doing, right? So then again you pass it through a band pass filter. So again cos A into sin B, right? That is sin A minus B. So that and then you are passing it through an low pass filter, so that 2 FC components and component will get eliminated there, and only you will have that difference of these two signals, that is theta component coming here, that is sin theta. Now you are again multiplying these two signals out here, right? Once you multiply these two signals here, you will find sin 2 theta, sin into cos. You have cos coming here from sin coming here from here, right? So sin theta into cos theta is sin 2 theta, right? So this is 2 theta. So you have this component, right? So you for small values sin theta is theta only, right? So you will find that the control voltage is proportional to theta. So you have a feedback loop right here. So if there is an error, so that error a voltage which is proportional to the error will be given to the VCO. It will correct the VCO. So this VCO will slowly slave to the correct frequency, right? So whenever there is no error available here, so there will be no correction voltage given here. So the VCO will oscillate in the desired FC value, right? Whenever this VCO for any reason, if it is not following FC, okay, it is following FC plus an error voltage out here, in this loop you will find a correction signal which is proportional to that error will be given to the VCO, and the VCO will correct itself so that to generate in FC. So these kind of things you can use in the receiver side to generate an carrier signal which is exactly in phase and exactly the same frequency of that what is being transmitted. So you can use it easily to demodulate your signal here, this local oscillator. So this entire local oscillator block is shown here. So if you have this FC perfectly matching with the FC which is here without this error, then the modulating signal will be without any noise. Okay, so this is kind of double sideband demodulator. And then you have the last kind of amplitude modulation which we are going to discuss is something known as a single sideband suppressed carrier, where even one of the sidebands either lower or upper is also removed, and we are only transmitting this. Actually this itself contains all the information which is required. So this FM is already available here. Okay, so this is an duplicate information which is available here. So we are going to remove that. Okay, so only thing is by removing this it will become transmission wise there is not an issue. Okay, it will save, again it will save power also. Further there will be decrease in power, right? The bandwidth also is now only FM. Okay, the bandwidth is also reduced here. If you see, it is not 2 FM, the bandwidth is reduced. Only thing is the demodulation becomes even more complex. Okay, so now if you have to understand, this is only the signal, only one of the sidebands is being sent. In this this example, only the lower sideband is being transmitted. So the bandwidth becomes FM and the power becomes m square by 4 instead of m square by 2 for a double sideband, 1 plus m square by 2 for an AM. Then it became m square by 4 in the 1 plus m square by 2, and now it is further reduced to m square by 4. Okay, for now the modulation power efficiency is also here 100, because there is only one signal which is being transmitted, which contains the information about the signal. So there is no additional carrier. So you can call the modulation power efficiency to be 100%. Right now, how to generate this signal? Okay, with only one. So if you have, this is how it is done. This is the modulation signal which you are doing a 90-degree phase shift, and you are getting it here. There are two product modulators. Here you are having the local oscillator carrier signal. So cos into cos A cos B, right? If you multiply these two things, you will get cos A plus B, right, and A minus B here, and you are doing here 90-degree phase shift, and you are doing within a sine. So sine A sine B, right? And then if you are going to add these two things, okay, when you use plus and plus, I think I missed out that equation. So if you add these two things, okay, you will get the you can just expand these two, right? You try to cos A cos B, you can write it cos A plus B into cos A plus B and A minus B terms. Similarly, sin A into sin B, if you write, and then if you add these things, you will get the upper sideband. If you subtract this, the plus minus is written here at any given time. Either you use plus or minus, not that you are going to use both of them out here, right? I just missed out that equation somewhere. Okay, otherwise it would be pretty clear. Okay, just you can do that yourself. You can just multiply these two equations, and you can multiply these two equations, so you will get S1 and you will get an S2. And then if you at any given time, like I said, you don't get carried away by this plus minus signal. Why it is given plus minus thing? You can either transmit the lower sideband or the upper sideband. So if you do addition, you will send the upper sideband. If you do the subtraction out here, you will send the lower sideband. Okay, so this is the single sideband modulator which we use. Okay, in the demodulator, again it is very critical to have a local oscillator which is which has got the exact phase. Otherwise this is going to create lot of noise out here. So you need a local oscillator which is exactly in sync with the data which is being transmitted here, right? So here there is no way that we can generate from this signal the local oscillator signal. It is going to be, so you have to have a separate scheme where the local oscillator is totally synced. So that is the disadvantage in this scheme. Okay, so whereas in the double sideband we could generate that signal by using a Costas loop, whereas in the Am modulation there was no requirement itself, so you could just do a square operation, right? For the so here it is just a summation of the three schemes which we have studied. So double sideband, it's a double sideband band. You also call it a double sideband Am model. You either call it as plain Am modulation, or you call it as double sideband full carrier. Okay, this is double sideband suppressed carrier, where there is no carrier, both the sidebands are there. Here both the sidebands and the carrier is also there. This is single sideband with suppressed carrier. Only one sideband is available, either a lower sideband or the upper sideband. So it is double sideband carrier along with carrier. It is double sideband without Am carrier, and here it is only one carrier. The bandwidth is 2 FM. Here the bandwidth is 2 FM. Here the bandwidth is only FM. Lesser number of channels in a given frequency range, because the bandwidth is high. This is also same, bandwidth is high. Here you can have more number of channels because the bandwidth is less. So if you have some megahertz range, you can pump in more number of channels out here. Okay, more power consumption, moderate power consumption, least power here the carrier signal is not there. Here one of the sidebands is also not there. Easy reconstruction at receiver, moderately difficult reconstruction, and it is very difficult reconstruction here. Okay, here you have more redundant data, moderately redundant data, and less redundant data. No need of synchronization. Tracking might be required. Here synchronization is essential. So these are the advantages and disadvantages of the three schemes which we have studied. So that's all for this. So I'll try to follow it up with one in LT-Spice. I'll try to do some simulation, and I'll make a module where you can see these waveforms and see the effect of change of RC and the modulation index and those things, and probably one more lecture on frequency modulation, and then super heterodyne receiver. It's a very interesting topic, and then probably the last one should be digital modulation concepts. So that will complete this series on communication systems. Okay, thanks a lot.